In the previous episode, we learned how linear regression predicts outcomes using a single feature. But real life is rarely that simple. A student's exam score depends on much more than study time alone. Although both students studied for the same amount of time, their actual performance will likely be very different. One variable cannot explain every outcome. Multiple linear regression extends the original idea by considering several independent variables simultaneously. Each feature contributes to the final prediction. Each coefficient measures the influence of one feature while keeping the others constant. Watch what happens when a single coefficient changes while everything else stays fixed. And Greek letter beta 0 is the baseline, the predicted score when every feature is 0. It plays the same role as the intercept from episode 1. Training is an optimization process. The algorithm repeatedly adjusts the coefficients, compares predictions with actual results, and continues refining the model until the overall error becomes as small as possible. The principle is exactly the same least squares idea from episode 1, only now the algorithm tunes 5 coefficients at once instead of 2. When training finishes, every coefficient has settled on its best value. Once training is complete, the model can estimate outcomes for new data. Every feature contributes to the final prediction according to the learned coefficients. 7 points for every study hour, a quarter point per % of attendance, 1.5 points per hour of sleep, and 1.3 per assignment. Added together with the baseline, the prediction is about 91. Not all features are equally important. Some variables have a much stronger influence on the outcome than others. One caution: coefficients can only be compared fairly after the features are placed on a common scale, because hours and percentages use very different units. Understanding feature importance helps explain how the model reaches its predictions. Let's recap. One feature is rarely enough. Multiple linear regression combines several features, each with its own coefficient. Training finds the coefficients that minimize the total error, and the fitted model weighs every feature to predict new outcomes. Multiple linear regression is used across industries whenever several measurable factors influence a continuous outcome. It remains one of the most widely used predictive models in science, engineering, economics, and healthcare. But what happens when the relationship between variables is not a straight line? In the next episode, we'll explore polynomial regression and discover how machine learning models can capture curved patterns found throughout the real world.